Hello, this is Sabir again. Uh, so I'm going to discuss today all about the eigenvalues and eigenvectors of a tensor. So here is the down. Um, eigenvalues and eigenvectors. Right. So what is eigenvalues and what is eigenvectors of a tensor? So say for example, it's very easy and it's very important concept, especially in every applied sciences, science, engineering subjects, because it is really very important topics and it has really very important influence on science and engineering or numerical sciences, something like that. Okay, so for example here, consider the tensor T, right? And a vector, so eigenvectors, so what is eigenvectors? Okay, so eigenvectors and eigenvalues are defined by the following equation. Say for example, v is an eigenvector of t, right? So v is a vector, right? And that vector is the eigenvectors of t. So we, if it is eigenvectors of t, then we write this in following equation. So tv equal to lambda v, right? So v should be eigenvectors of tensor t if this follows the following equation. So what is alpha? Alpha is nothing but alpha is eigenvalues. Eigen. So v, so six kinds of transformation. So t is a tensor that transforms t into something that is alpha v. So here v is parallel to itself, right? So v is parallel to itself, and alpha is scalar values and it's eigenvalues. This is called eigenvalues, and v is eigenvectors. Eigenvectors, right? So any tensor has infinitely many, infinite number of eigenvectors. So, for example, I can give you an example here. Say, for example, if you consider this here, say a tensor, say for example, a equal to 3, 1, and 1, 3, 1, 1, 3, and its corresponding eigenvalue. Say for example, u is eigenvalue, then 4 minus 4, right? 4 and 4 minus 4. Then you can write according to the definition here. So we can write down here a b. So what you can write down, 3 1 1 3 1 3 times 4 minus 4. So what you can write down here, so 3 times 4 12, 3 times 3 times 4 here 12, plus 1 times minus 4, so that is minus 4, right? And again here, uh, 1 1 times 4 equal to 4 minus 12, so it is 8 and minus 8, right? 8 and minus 8. So we can write down this in the following format here. So you can write down this 2 times 4 minus 4. Say, see here, the 4 minus 4 is exactly same as the 4 minus 4, and 2 is the eigenvalues. 2 is an eigenvalue here in three-dimensional case. Eigenvalue, and this is the eigenvector. So, it is proved that this eigenvector is same as this, like, yeah. So we'll go to the more details all about that characteristic polynomial equation, how we can find the characteristic polynomial equation, or how we can find the eigenvalues, right? So so from the definition we know that, say for example, a is a is a tensor, right? And v is the corresponding eigenvector. So we can write down according to the definition, lambda v. So from where we can write down av minus lambda v equal to 0, right? Yeah. So we can bring out the eigenvectors from this, so we can write down a minus lambda, we bring this v, this is there, right? So we can write down this lambda, say we can write this lambda equal to I lambda, right? Because I is identity matrix, so which transforms any vector to any vector itself of that, right? So it's same, equal to the same, so alpha equal to lambda, so we know very well from the identity matrix, so we can write down here a minus I lambda is equal to 0. So these eigenvectors, and these are changing the color, so it will be better for you to visualize here. Yeah. So these are the identity matrix, and these eigenvalues, and A is a tensor, and the eigenvectors, right? So I'm getting the eigenvectors, eigenvectors, these eigenvalues, eigenvalues, and these are the identity matrix, identity matrix, identity tensor, matrix or identity tensor, or tensor, whatever, and this is our original tensor, the original tensor, right? So we can write on the following equation. So definitely eigenvector should not be a zero vector, so this always be a non-zero vector, right? So this should be a non-zero vectors, because if it is a zero vectors, then there, if say for example if it is zero vectors, then zero vectors times any tensor will be zero, so there is any tensor or something like that, so it cannot be exist. So this must be a non-zero vector, so it's the linear algebra equation, something zero vector, it's a non-zero vector, so this must be zero, but it cannot be zero until unless it's determinant, but its determinant can be zero. So determinant of determinant of A minus identity matrix, sorry, matrix is equal to 0. What we can write down in short notation from I lambda, something like that, yeah, 0. So how we can write down this equation here? So we can write down this. We can write down this in here. So A, say for example here, say here equal to A11, A12, A13, A21, A22, A23, A31, A32, and A33. So here, so so we need to find out what is the value of alpha, right? So we know the identity matrix here. Identity matrix 1 0 0 0 1 0, so 0 0 and 1, this, right? And alpha is alpha corresponding eigenvalues we need to find out, right? So we can write down the following equation there. So so here A11, A12, A13, A21, A22, A23, here is A31, A32, A33. So this is the tensor minus lambda, so 1 0 0, so 0 1 0 0 0 1, so the determinant of that is equal to 0, right? So we can write down, so if you do not write it here, so we can write down lambda, right? Lambda here, lambda here. So if we subtract these vectors to this, so we can find out that we can write down this equation in this following format: a11 minus lambda, so a12, because a12 minus 0 is equal to a12, a13, a21, a22 minus lambda, a23, a31, 3 2 3 3 minus lambda, right? So this is the tensor, and the determinant of that is equal to 0. So something like that. So from there we can, so from we will have this will form the equation or something like that. So this is the characteristic equation or polynomial equation, characteristic polynomial equation. So the root of this, so as the three-dimensional, right? So we'll get alpha cube or something like that. So we'll get three roots here. Say for example alpha 1, alpha 2, and alpha 2. So these are corresponding the eigenvalues. We'll get the eigenvalues, something like that, right? So this whole form or this whole equation is called the characteristic equation. These are the called characteristic equation. I'm going to change the colors so it will be more visualistic for you. This is called characteristic characteristic equation. So I'm going to give you an example how to do that. Okay. Say, um, say for example here we have a tensor a equal to 200 200 0 3 4 0 4 9. So for example here we have the tensor here, and we have to find out its eigenvalues. So how we can find out its eigenvalues? So we can write down this determinant a minus alpha I, right? Here I is the identity matrix, and the I is the eigenvalues of this should be 0. So what is that? So I can write down, so determinant here. So determinant 2 0 0 0 3 4 0 4 9, right? Determinant minus alpha 0 0 0 alpha 0 0 0 and alpha, right? So here, and this should be 0. So we can write down, so from there we can write down 2 minus alpha. So from 2 minus alpha here 0 and 0 0 3 minus alpha here 0. So we can write down here again 0 4 9 minus alpha. So something like that is equal to 0. It's determinant is equal to 0, right? So you can write down from here that so if you find out on the determinant of that, then it will 2 minus lambda uh, 3 minus lambda times 9 minus lambda minus 16, the whole term, that should be 0, right? So from there we can write down here minus alpha cube plus 14 alpha square, sorry, 14 alpha square minus 35 alpha and plus 20 equal to 0. So it's a polynomial equation, right? Third order polynomial equation, and is the power of alpha is cube here, right? Cube here. So we'll have three roots of alpha. So say for example alpha 1, alpha 2, and alpha 3. So if we solve the equation, we will get this the roots of this here. Alpha 1 equal to 2, alpha 2 equal to 1, alpha 2 equal to 1, and alpha 3 equal to 11. So we find out our eigenvalues of that here, right? So eigenvalues here, something like that. So we find out our eigenvalues or something like that. And the corresponding eigenvalues, how we can find the eigenvectors or something like that. So there are infinitely number of eigenvectors of that, according to say that. So for example here, if an eigenvector should be a non-zero, so we have already seen that eigenvectors must be a non-zero, because if it is zero vectors, then zero vectors times any tensor should be 0, so it cannot be exist, right? So say any non-zero vector, say 1 0 0 transpose of this can also be a eigenvectors, and this can also be an eigenvector, say 0 2 minus 1 you can, and there are a lot of infinitely number of vectors, something like that. So say we can if you want, then we can test that. So what is our main vectors? 2 0, yeah, we can test, say for example here our so you can change the color, it will be better for you to do that. So if I write down here a, right, a equal to say 2 0 0, say 2 0 0 here, 0 3 4 0 4 9 0 4 9, right? So this times this, this times this times this, so transpose of that, right? So 1 0 0, our eigenvalues, our what is our eigenvalues? Eigenvalues are 2 1 and 11, right? So 2 1 and 11. So we are expecting that v should be like this. So say for example here we can do that. Say, let's say here 2, so this times 0 0 0, so this 1, so this should be 0, right? And similarly this and this should be all the 0. So if we multiply this, right, and if we multiply this like this, so we found this. So if we um, find out here, then we can I think I'm making some error now. Now we can, so find out this 2, yeah, this 1 0 and 0, right? So we've got this. So these are our corresponding vector, something like that. So we can find out. So we can find out there are a lot of eigenvectors or something that are they're infinite eigenvectors, and the eigenvectors say here are three component eigenvectors, right? So three component eigenvectors depend on three direction. So it is here. So if we draw a coordinate here, then it will go one with one in it to the x-axis. So this confidence. So according to this 2 0 minus 1, then 0. So another eigenvectors here b2, say b1. So this b2 is say, so the direction of the eigenvectors v1 is from 0 to that. So its direction is something like that. So what is the direction of that? 0 2 minus 1. So 0 here is x 0, 2 means 1, 2 here, 2 say here, and minus 1 is here, minus 1 is here. So it will be something like this. So its direction should be something like this, right? Minus 1. So it's a three dimensional, right? 6 7 1. So it's nothing but that. Yeah. So it's very simple and it's very easy to find out the direction or something like that. Okay, so I hope you have got or you have understood all about the eigenvalues and eigenvectors of a tensor. It's similar to the matrix or something like that. So I'm going to stop because of my time limitation here. So in the next lecture, I'm going to make you understand what is the principal values and principal direction of a real symmetric tensor. So it is a really important for you guys if you are interested to do research on applied sciences or something like that, especially in geodynamics and geophysics, to identify a fault or fault detection or a stress or a strain analysis of a fault or fault. So you must have to know what is the principal direction and the corresponding principal values. Okay, thank you guys, and I'm going to see you on the next lecture.